Welcome to this explainer. Today, we're unpacking what is usually considered a notoriously intimidating engineering syllabus, signals and systems. But don't worry, we aren't going to be staring blindly at whiteboards full of Greek letters. No way. Instead, we're looking at a completely brilliant, thoughtfully designed 14-week curriculum that takes all that abstract math and turns it into the tangible reality powering our digital world. Seriously, from the Wi-Fi you're using right this second to the suspension in your car, it literally all starts right here.
Okay, let's dive into this. There is this fantastic quote that sets the stage perfectly. A signal is a letter. A system is the post office that reads, sorts, and forwards it. This establishes immediately that we aren't just looking at dry equations today. The content of the letter doesn't actually change, right? But how and when it gets delivered absolutely does. This is just a brilliant simile that gives us a real physical anchor for the math.
So here is our roadmap for the explainer today, which actually mirrors the 4 major arcs of the semester. We'll kick things off with the course's active learning approach. Then we'll travel through the time domain, the frequency domain, transform methods, and finally finish up with a capstone on sampling and aliasing.
All right, stop number 1, the active learning approach. Now, what's really interesting about this approach is how it anchors incredibly complex concepts in real life way before anyone even touches a whiteboard marker. It's a pedagogical playbook heavily rooted in active learning. This ensures students don't just passively sit there and watch math happen. Every 2-hour session blends short instruction with a very consistent 5-part teaching rhythm. They always start with a recap. Because let's face it, confusion usually comes from a missing link, not the new material. Then comes that real-life anchor, followed immediately by live polls to catch any misconceptions early on. Next, they use a think, pair, share exercise to get students actually working the math themselves, and finish the whole thing off with a formative, low-stakes quiz. It's an amazing way to make abstract math accessible through constant active engagement.
Moving right along to Part 1, the time domain. This covers weeks 1 through 5.
So, to really understand signals, you first have to categorize them. Think of a continuous time signal kind of like an ECG heart trace on a medical monitor. It's flowing, right? Now contrast that with a discrete time signal, like a daily stock closing price, where you only get a specific value at specific set intervals. Using these relatable real-world examples helps us instantly visualize the difference between the 2 core types of signals engineers are dealing with every single day.
Okay, so by weeks 4 and 5, the course tackles a massive hurdle for students: convolution. Mathematically, this is defined as combining an input signal and an impulse response to produce an output in what's called linear time-invariant systems. So, the crucial point here is that if you know a system's impulse response, you can predict exactly how it's going to react to absolutely any input you throw at it.
But let's ground that math, because it sounds heavy. Convolution is simply an echo. Just imagine you're shouting into a huge cavern. Every past shout, which is your input, leaves a fading echo, which is the impulse response. So what you're hearing right now is the sum of all those echoes arriving together at the exact same time. This is literally the exact math behind room reverb in music production, or how financial analysts apply moving averages to smooth out those super jumpy stock prices.
All right, let's shift into Part 2, frequency domain. We are now in weeks 6 through 10. Now we're leaving the timeline behind to uncover some hidden harmonies within the signals. To introduce the Fourier series, the course uses this incredibly vivid simile. Fourier series is a prism splitting white light into a rainbow of pure colors. It's basically a mathematical recipe. It explains how you can completely decompose complex sounds, say a piano playing a C major chord, into a simple sum of pure sinusoidal tones. It tells you exactly how much of each pure note to bake into the signal to recreate it perfectly. How cool is that?
But as with most things, this mathematical prism isn't perfect, and that brings us to the Gibbs phenomenon. This is a persistent mathematical overshoot that happens near a sharp jump or a discontinuity in a signal. And, live polls in the class frequently reveal a super common misconception here. Students naturally assume that if you just keep adding more and more harmonics, this little overshoot will eventually just disappear. But it doesn't. It just gets narrower.
And this brilliantly illustrates how these highly abstract theorems actually show up in our daily lives. I mean, you've almost certainly seen the Gibbs phenomenon in reality without knowing the name for it. Have you ever noticed that frustrating, kind of blurry ringing artifact right next to really sharp, high-contrast edges in a highly compressed JPEG image? Or maybe you've heard a strange pre-echo in poorly filtered digital audio. Yep, that is the Gibbs phenomenon at work, just stubbornly persisting near sharp edges. As we explore this frequency domain, I really have to ask you the same question posed to the students. Can an ideal brick wall filter actually exist in a real causal system? Basically, a filter that perfectly, flawlessly cuts off all unwanted frequencies and lets all the desired ones through without a single mistake?
Well, spoiler alert, the answer is no, mostly because of pesky physical limitations. To break down this trade-off, the syllabus uses a highly relatable club bouncer simile. The passband? Well, that's the height range of guests allowed into the club. The stop band consists of all the guests turned away at the door. But no real-world bouncer has a razor-sharp cutoff. Every single one of them has an ambiguity zone, the transition band. So real causal systems simply cannot have instantaneous brick wall cutoffs.
Moving into Part 3, Transform Methods, weeks 11 through 13.
So, how exactly do engineers handle unruly or exponentially growing signals that standard Fourier analysis simply cannot cope with? The answer is transforms. The Laplace transform effectively adds a mathematical safety harness to continuous signals so we can analyze exponential growth without the math just totally blowing up. And then we have the Z-transform, which is its discrete time twin. This one evaluates stability by taking a slice through what they call the Z-plane cake. These transforms are absolutely essential for real-world applications. Think of keeping a drone stabilized in midair or coding slick digital audio effects.
One of the absolute primary uses of these transforms is analyzing a system's poles to instantly reveal its stability. And the best part? You don't even need to run complex simulations. Think of it like a spinning top. If a pole lands in the right half plane, the top is tilted enough to topple over, meaning it's unstable. But if it lands in the left half plane, the top is steady and self-correcting. It is a brilliant visual shortcut for control engineers.
Section 5, Sampling and Aliasing, our Week 14 capstone.
Let's move to the end and see how this all builds up. This final week pulls the entire semester together to show us exactly how the analog world is safely digitized. First, you have the proper Nyquist sampling rate. It's basically like flashing a strobe light faster than twice the fastest motion you were trying to capture. But then, on the flip side, you have undersampling. This creates the famous wagon wheel effect you've probably seen in old Western movies, where a spinning wheel appears completely frozen or even looks like it's rotating backward. And you know that wagon wheel effect? That is exactly what aliasing is, a distortion where an undersampled high-frequency signal masquerades as a lower alias frequency. Essentially, if you sample too slowly, you are fooled by a slower fake. Engineers have to actively combat this with anti-aliasing filters. Actually, this is the exact reason why high-end digital cameras use optical anti-aliasing filters. It prevents those weird swirling moire patterns from showing up when you snap a picture of fine striped fabrics.
So let's quickly recap this really beautiful chronological progression. Weeks 1 through 5 securely anchor us in the time domain. Weeks 6 through 10 pull back the curtain on the frequency domain. Weeks 11 through 13 introduce transform methods to handle unstable systems, and week 14 ties the whole shebang together with a sampling capstone. It really is a true structural triumph of curriculum design that turns high-level, intimidating math into a highly practical toolkit. Which brings us to our final thought for today. The very next time you stream a high-definition video or send a quick voice note to a friend, I want you to ask yourself, which invisible mathematical systems are out there faithfully delivering your signal? Because just beneath the glass of our screens, it's this exact architecture, the time domains, the Fourier transforms, those carefully chosen sampling rates that is constantly and silently running our modern digital lives. Thanks so much for joining me for this explainer, and definitely keep asking questions about the hidden systems all around you.